Good afternoon, everyone. Thank you so much for coming here over your lunchtime to participate in our final brown bag talk in our series on Delta ecosystem services. Just a little background on Ben Bryant. He's a multidisciplinary scholar practitioner working to integrate academic findings into practical on-the-ground policy and planning efforts. He has a background in environmental and economic modeling for decision support with a focus on water management, ecosystem services, and decision-making under uncertainty. Ben received his Ph.D. in policy analysis from the Rand Corporation's graduate school, previously worked in international development for the U.S. government, and is currently a postdoctoral scholar based at the Natural Capital Project and Water in the West, two applied environmental research groups at Stanford University. All right, Ben.
Thank you for having me, everyone. So I have sort of a two-part talk, which the combination of them I've just lumped under the title Adventures in Decision-Oriented Ecosystem Services Modeling. And so the first half, I listened to Van's talk last week. I don't know how many people were here for that, but it sort of teed up some discussion of the modeling suite of process-based ecosystem service models that we have at the Natural Capital Project. So I'm going to spend a little time talking about that, and then in the second half, talk about what was more the original focus of the abstract on this idea of spatial targeting for investments in multiple ecosystem services under uncertainty, and think about how that can apply to the Central Valley, which I think we recognize is fairly connected to the Delta. But so there's the light. All right, cool. So just quick background on the two groups that I work with. I sit jointly between the Natural Capital Project and Water in the West, and I'm not going to read this text here, but they both have in common that they are very decision-oriented groups that are trying to connect academia and the policy or other decision-making world. And so one area, and what they do is sort of in the title. Natural Capital Project focuses on ecosystem services explicitly, and Water in the West is more water-oriented. And one connecting point, of course, is hydrologic ecosystem services. So, and that's a lot of what I look at, whether it's forest management, connection to water resources, or agriculture and other impacts on sediment or water yield and things like that. So. I think, so this is the third, I think a lot of people probably knew what ecosystem services were to begin with, and since this is the third brown bag in the ecosystem services series, I figure I don't need to do a lot of explanation on that, but there are a lot of different ways that people do ecosystem services modeling and connect it into decision making. So I wanted to kind of spend a little bit of time talking about how we tend to do it at the Natural Capital Project, and this idea of a production function approach to ecosystem services, because it kind of has implications for how that gets operationalized in real life. So just to be explicit, what we're talking about is this idea that we're interested in changes on a landscape or seascape, for example, and we want to understand how those filter through all the way down to impact on people in terms that people care about. So as a classic example, you might have some either judgment or regulation or private decision to restore riparian habitat in an agricultural zone or something. And so what that does is it translates into a change in ecosystem services structure. So whereas before maybe you did not have a lot of riparian buffer, now you do have that in between your agricultural land and your stream, for example. So that's this change in structure. And then when you have that change in structure, that leads to a change in how the ecosystem service is functioning and what processes are going on there. So it's going to change the process of water filtration from the agricultural field to the stream, and it may also help promote retention of soil, for example. And then that, in turn, translates to things that people actually care about. So people, whether they're recreational users or water utilities, might care about the sediment load in a stream. And if you're the farmer who is working that land, then you might care about the soil that's retained, you might gain a benefit from having better soil retention on your land, and then also you have this, conversely, a direct cost where you had area that was in production before that is now no longer in production. So there's kind of an impact in both directions there. And then the last step is translating those kind of biophysical outcomes that people generally have reason to care about into metrics that resonate with them. And so people often assume that we're always talking about monetary values, which is something that does have a lot of policy relevance a lot of times, but it's not always the case that we do that. But just to be concrete here, so one example might be that the change in sediment load in the stream or concentration would affect the treatment costs that a water utility needs to pay in order to deliver water of adequate clarity to its customers. And similarly, the soil retention trade-off with cropping area will affect crop revenues for farmers. And then you can also have, so those are monetary metrics. You might also have a broader kind of what we call benefit relevant indicator is the lingo term for number of people affected by stream clarity, for example. So if you have a lot of people going to visit a park with a river, they might prefer if that water is cleaner looking. So that's the overall process. And in general, one aspect of this, especially since we're looking at this this issue of ecosystem structure, it means that where matters. So where matters for the activity, if you're looking at mouse, yes. So if we had put this vegetation in the middle of this field, the impact on all of this stuff downstream would obviously be different and probably less. And similarly, where matters in terms of the beneficiaries, where people are. So undertaking restoration or enhancing the environment will have a bigger impact if it's done in a place that lots of people are going to experience it, all else equal. So that's kind of the overall framework and kind of motivating approach that we tend to take and try to connect this entire chain. And I'll say I'm totally fine with interrupting clarifying questions. Big picture philosophical questions can wait till the end, but feel free to jump in if there's something that's not clear. So to give a specific example of this, one of our goals is that this process needs to be something that people can actually do in a reasonable time frame in order to feed into decision processes. And so part of that means translating the science of describing those relationships into software for people to use in a relatively easier way than doing something custom every single time. So in this example, we have a demand that we've witnessed from groups that we work with. They're called water funds. I think Van alluded to them last week. But essentially, the rough idea is that downstream users in a watershed recognize that the actions and stewardship of upstream users affects characteristics of water flows and water quality that they care about. And so they don't directly pay on an outcome basis for water, but just generally put in funds to support stewardship of the upper watersheds. And one thing that they often want to know is what, there's a lot of things people care about. They care about water quality, and they care about avoiding flooding and things like that. And they also care about having, they often care about high base flow to get through the dry season. So when you have more water throughout the summer, that's kind of nice. And so a question arises of what should I be doing in this upper landscape if I care about promoting that outcome? So this is a common interest. And so our hydrologists worked with some collaborators and developed a model to essentially describe this in space. So answering the question, where in space is more or less contributing to base flow? And then that's translated into code by our software team, and then that's wrapped up into kind of an executable package in Windows that you can just kind of install. And that then gets you maps of where stuff is happening on the landscape. So in this case, this is a map where the darker areas are telling you that those areas are contributing more to dry season base flow relative to areas that are lighter colored. And so from a decision standpoint, you might want to prioritize those areas from being converted to impervious surface cover or something like that. And just to, you presumably can't actually read this, but just to give you a flavor of what's going into these. So some of these inputs, this interface is essentially pointing to files that are inputs to the model. And so many of them are spatial, so things like digital elevation maps. What's in there? Almost all of our terrestrial and hydrologic models require land use land cover maps and things like that. And then there's some hydrologic parameters and other things. So the model essentially takes everything you see there, feeds it through the equations that are described in that paper, and then spits out maps like the one direct. Cool. So we've taken that approach for a lot of different models, which vary in kind of the level of rigor that's gone on it, and also in the level of sophistication. So some of our models have gone through that process of kind of this idealized process of user demand, peer-reviewed publication, software implementation, iteration, et cetera. And then other ones are closer to kind of simple lookup tables, for example, that connect tables of, say, carbon storage with land cover types or things like that. And in general, this is kind of always an ongoing demand-driven iteration process there, where models that have weaknesses that are a problem for users get more attention based on the use cases and engagement that we're doing. So you can go to our website and kind of look at descriptions of all of these. Obviously, there's too many for me to spend time on individually. But and then just to say that we're most associated with this INVEST suite of models, and that's kind of our term for the actual ecosystem services models that we have. But we also develop a lot of helper tools in response to common analytic tasks that people have. So, for example, this geoprocessing over on the right was essentially a spatial processing tool set that was addressing a lot of common needs that we had for INVEST and other models, so we could still use that without relying on like ArcGIS or needing to link to Q or things like that. And then we have a bunch of other things as well. So, and to give a picture of where we're trying to go, I think that's all of the arrows. All the arrows. One more. Cool. So this is kind of where things are now, to give you a sense of the structure and how it can be used or integrated into other projects. So all of this cascade is the individual models, and there's a Python API that kind of power users can use to interact with models and build interfaces or custom workflows around them. And on the very right, we have the user interface, like you saw, that's kind of a single run, set it, go, look at the output type of thing. And then down here we have all of these models need a whole bunch of data. And that is kind of annoying, both to run models lots of times and to gather data to run them. And so the general direction that our idealized, often the future vision that we're trying to move towards is generally all about making the things that are not science and thinking a lot easier and more automated. So being able to run models faster and or run them off of your computer so you don't have to wait around for a day or two while your computer does a bunch of runs. A big part is curating a lot of the commonly needed spatial data, which is one of our general, even our own analysts and users often complain about the amount of effort that's required to fill in all of to identify in all of the parameters and maps and things that are necessary to run the models. And then a lot of the kind of trade-off analysis and spatial optimization and things like that essentially involve running models lots of times and processing the results in a way that's useful for your decision at hand. And so we're trying to make that easier as well. And I'll just mention that we are not the only people making ecosystem services models, of course. And about every year or two, somebody writes a review paper. This is a recent and fairly thorough one, if you are curious about other options in there. Many of them tend to focus on one particular kind of niche or suite. So eco-hydrologic models there's a number of those, and then there's carbon cycling models and da-da-da-da-da. So I encourage you to look around for whether models meet your needs. They all vary in terms of the data requirements, the complexity of the processes represented, and things like that. And then I also just wanted to mention, partly because it was touched upon last week in the talk, about this issue of how you actually get this information utilized in decision making. And so at NatCap, we kind of have a couple different pillars that we're built on. And one is doing science, and one is kind of translating that science into approaches and tools that people can use. And then there's this aspect of building success and sharing that success. And so the idea is that doing all of those are essentially both motivating and reducing the barriers for people to utilize natural capital information in their decisions. And I wanted to talk about, most of what I was talking about was this user-friendly tools part of it. But I did want to mention that a lot of what we do and what we found effective, which is not just us, but a general finding from the literature, is that iterative engagement and kind of co-production, co-development, et cetera, is both an effective and important thing to do when you're trying to actually get your science taken up. We sometimes joke that we should have a drinking game for when you put co in front of something, but it's sort of true that co-development, co-production, it's all co-creation, it's all important. And so just to give an example of that without going into a lot of detail, we're working with a couple different groups right now on looking at ecosystem service impacts of forest restoration in the Sierra Nevada. So the general question is, you're probably aware of the general narrative of forests here have been fire suppressed for a very long time, and that you may have benefits from restoring them to a more fire resilient state. And so one question is, what are all the different ecosystem service impacts that could come from that? And depending on who you're talking to and trying to convince to care or take action or pay, they may all have different metrics. And so that's one of the things we're doing with partners is, actually talking to them. So it's not just writing kind of a social welfare assessment of what the net economic gains might be, for example, but going to water utilities and being like, okay, here is how we think hydrology might change or fire risk might change. What does this actually mean for your bottom line in terms of the fact that you're constrained by all these legal and infrastructure constraints? Does this speak to you? Does this resonate? What type of analysis would resonate if what's coming out of our models does not? So just that point of every stakeholder may have different things that they care about, and so the more you can plan to address things to each stakeholder, the more likely you are to get things taken up. All right, going to take a sip. Anyways, this is the end of part one. Any questions while I take a sip of water?
Isn't that like a suite of tools or not? So what I gather from a presentation is Invest is a suite of tools that might fit a bunch of different purposes. And my question, what I'm trying to get my head around is, who is the target customer for these tools?
Sure. Well, I guess there's the target audience. So first, they're all free, so I'm not trying to sell them. But in terms of target audience, I guess there's the tool user, and then there's the audience for the analysis. And so sometimes so we work with essentially every sector. So we've worked with like Unilever Corporation to help figure out environmental impacts of their sourcing decisions, and they're trying to bring those tools into their own kind of life cycle assessment workflow. A lot of work is with conservation organizations wanting to not just preserve habitat, but also think about how to generate other ecosystem services as well. Development planning and spatial planning exercises. So in terms of the audience, it's essentially all decision makers who have whose decisions are affected by and or affect spatial outcomes, basically. We have on our website, we have a where we work map that kind of describes a lot of the different engagements, but it's essentially governments, NGOs, and the private sector. Yes.
Do you have examples where when you identified some really critical legal or other infrastructure constraints, where your target audience was actually policymakers and legislatures and Congress and those kinds of folks?
I think the answer is yes. I'm trying to think off the top of my head. I mean, I guess the most high-level success case of that we were only a small part of, but was there's a OMB White House memo essentially requiring federal agencies to start considering ecosystem services in their decision-making. And so that's a case where you kind of demonstrate the value of incorporating this information versus ignoring it, and then eventually that percolates down to a policy change that requires decision processes to take that information into account. Another example that, again, is not our work entirely, in this case, very little, but there's an assembly bill in the last year or two that essentially let utilities and municipalities put natural capital of their watersheds on their books as an asset, which kind of changes how they can manage and raise funds to deal with those. So, yeah, I think policy is, a lot of times our specific engagements are kind of micro-level decisions, but there is this sidetrack of influencing the policy to allow for that to work. All right. So now I'll kind of switch gears a little bit, but talk about in the back of what's being discussed here are the ability to draw on all the types of ecosystem service modeling approaches that I was just discussing. So how can we fit that into a spatial planning context? So I spend a lot of time thinking about this general question of we think in landscapes, and the landscape structure is providing benefits to people, and maybe it's in the process of being degraded, or maybe it's being subject to external forces, et cetera. And we want to know where on the landscape should we target changes that we can control in order to achieve multiple objectives. So those changes might take the form of changing irrigation practice or what crops are growing, or that might involve restoring degraded land, for example. And the objectives that we're talking about can be very specific, like meet minimum in-stream flow requirements, or could just be broad, like agricultural livelihoods or something like that. So I find this is a very interesting question that I think is perhaps overly general, but being very general, it has a lot of application. But one point that I think is not always considered is that our ability to characterize these systems and predict the impact of our decisions is limited by a large number of uncertainties. And this is a map of Africa, but the same issue arises for California if you think about different land cover maps. This is just showing that in general, we often have a lot of disagreement and inability to perfectly characterize even the starting state that we're working in. So as I mentioned, the land use land cover maps are very important inputs to our models, and given that there's uncertainty and disagreement in those, it's important to see if that actually matters. And not only do we have imperfect knowledge of where we are now, we're also generally not very good at predicting drivers in the future. So this is an example of demand forecasts for water demand in Seattle, where each line is a different forecast from different points in time, and you can see how good they are. And you can imagine that planning for those forecasts would lead to some significant error and costly policies. And then we also have an imperfect ability to describe how the system will evolve, which is a function both of parameters that go into models and also the structural form of those models. So on the bottom here we have, these are all the numbers you would need to put in if you wanted to run all 4 of the INVEST water models. Each row is a land cover type, and then each column is a parameter. It's a little unfair because most of the screen is taken up with our seasonal water yield model, but either way, these are a lot of numbers that that represent physical processes, and suspiciously many of them are the same exact number when we know that that would not really be the case in real life. So you kind of need to figure out what all of these are. And then you also don't know your physical system. For example, with this, in the upper right, you have a groundwater system, which in general we are not able to characterize super accurately. And so we don't necessarily know perfectly how actions on the surface will percolate down into sustainability considerations and flows within that aquifer. And then lastly, we also have imperfect knowledge of what people actually care about. So we haven't know generally the types of objectives people have in mind. They might care about recreation and water quality and species preservation and, of course, agriculture. But our way of kind of gauging and measuring these preferences is always imperfect. So it could come from market behavior, which is what economists tend to focus on, and reveal preference in markets. And it can also come from voting and ballot measures and things like that, or focus groups. But each of these is like, they have gaps in information and characterizing how people are willing to trade off different objectives and what's actually important to them. And so to a little more explicitly connect this to California, I think we would agree that most people, especially in the Central Valley, there's this interest in agricultural livelihoods, having clean water, not polluted groundwater, no mining waste in your streams, et cetera. So these are some of the many things people care about. We're also subject to a lot of these exogenous uncertainties, like demand for solar, or whether almonds are going to continue to be very important or not. Climate change is, of course, affecting how agriculture works. And then, earthquakes and structures of levees and things like that are some more significant one-off shocks. And then there's things that we can do in the land management, land use planning, conservation space, for example, including adjusting cropping patterns, changing land use in terms of zoning, targeting restoration, the parameters of groundwater sustainability plans that are being implemented or developed through SGMA, and then also state infrastructure decisions. And one thing I wanted to point out is that even non-spatial actions still generally have spatial consequences if we're talking about land use. So a water price or a carbon price translates into different spatially varying suitabilities for different types of actions on the landscape. So often things are spatial even when you're not thinking in those terms. And so a question that we're kind of interested in, and we've noticed that about 1 million different NGOs are interested in, is that a lot of people are asking this question of, there's a lot of change going on in the Central Valley, and there's a lot of programs that recognize ecosystem services as something to be managed for or incentivized, while also the agricultural economy is under potential threat from both climate and water availability. And so what can we do about that, and what's going to be robust to these many uncertainties and help achieve all of these kind of high-level objectives? And yeah, I essentially said all those before, so I'll skip that. And so the general, connecting this uncertainty angle with this decision framing, the general approach that I advocate is that we do need to use models because they contain a lot of information, but also we need to be very cautious and humble about putting weight on any particular model run or even any model or set of models given all of those uncertainties, because any single run essentially captures just one particular set of assumptions about the starting state, how things evolve, and what external forces might act on that system. And similarly, if you're optimizing for some particular outcome, that's one set of preferences there. And so the high-level idea is that you have this workflow where you have some kind of system models that links management options and uncertainties into outcome metrics that you care about, but you want to explore that extremely thoroughly to kind of build insight about relationships rather than trying to just pick the best answer or trust a model. And so to be a little more explicit on what this looks like in practice, yeah, you can see that, cool. So some of our work and what we're thinking about trying to integrate our work with that of some other groups. Essentially what we do is generate maps of recommending where to do what on a landscape, and where you do what, or what you do where, varies depending on the things that are highest priority to you. So in this example, we have a trade-off curve where each dot represents a landscape, and if you care most about water yield, then in this case it's saying do terracing in these, this is in Africa, so sorry, it's not super relevant. I don't think we need to be terracing the Central Valley. It's saying do terracing in these places where you see pink. But if you care most about sediment retention, maybe you should focus on mitigating a bunch of dirt roads that you have. And so the point is that each priority combination that you pick in terms of your objectives leads to a potentially different landscape that you would want to implement. And then you can do that and explore the implications. So you can say, maybe across all of my potential preference combinations, what should I be doing no matter what? So this map is showing where you see dark blue. It's showing there's high agreement that regardless of your weighting on, say, sediment versus nitrogen reduction or water yield, you should engage in a certain action in those places. And you can generate these maps more adaptively as well. And so one way to kind of tie these all together is this idea of sometimes it's called an XLRM framework for uncertainties and policy levers and relationships, and then your metrics. And so the idea is you just want to, this exercise of actually even just tracking them in the first place can be helpful in illuminating. And then it's also good to revisit your analysis, even if you aren't quantitatively able to speak to all of these issues. Being able to kind of go back and forth between your qualitative assessment and your quantitative modeling can be very helpful. One general challenge, though, when you're trying to build a system to translate, actions on a landscape into outcomes, is being able to know where to draw the boundaries of your system, because everything, especially with water, everything is connected, and so it's nice if we can manage within, say, a groundwater sustainability agency or the Delta without having to do all of California. And since California gets some water from Colorado, hopefully don't need to include the entire American West, et cetera. So this is kind of a general challenge that we always need to deal with. And putting those together in this sort of iterative process, one of the things we can do is generate these frontiers that I was talking about, or trade-off curves for different objectives that we care about. You can do that in many different states of the world. And you can use economic valuation or other kind of participatory or multi-criteria processes to filter down into relevant potential solutions. And you can take those and you can test them again against other future states of the world and see how well they do. And then they'll probably not do very well. So a land use policy that you develop that assumes we've augmented water supply and that you have highly reliable surface water will probably not do very well in a world where climate change is more severe than we anticipated and we did not build more storage, for example. And so you can kind of test failure scenarios and try to augment your decisions in a way that will make them more robust to different states of the world. And of course, it's always required that you monitor and revisit things. And I'll just mention that this flowchart that I have here is kind of the spatial version of, there's a suite of methodologies under the rubric of decision-making under deep uncertainty that have kind of emerged in the last 10 or 15 years that now has its own society and a broad set of methods. So I encourage you to check that out. And just to give a flavor of what that might look like. Is this the real one, or is that a screenshot? Yes. Okay. So just to give a sense of this dynamic angle, this is a dashboard where we did essentially what I was talking about of running multiple ecosystem service models against like 800 different parameter and weighting combinations, essentially. So if you see over here, every single dot is a landscape. And these are for 3 different services. One is water yield, one is sediment retention, and one is soil loss, which are closely related, but they're affected in space because you can lose soil without it going into a stream, potentially. And so up here we have all these slider bars that let you kind of dynamically explore what you might want to do on the landscape changes depending on the assumptions you make. So over here are weighting on different objectives, and over here are different kind of either parameter numbers or scenarios that you can kind of explore policy performance in those. And so right now it's showing every single thing, but what you can do is say, okay, I really only care about cases where I have high water yield. And that shows you the cases where you have high water yield, and you can say, what does my portfolio look like in cases where I have high water yield? And so this is showing you, this is where you should do things if you're most interested in high water yield. And you can flip that and say, what if I care mostly about sediment? And it'll show you, where you should do things if you care mostly about sediment. And so the idea is that you can use this type of display in a sort of participatory process where you can think through what these different scenarios actually look like in the real world and overlay the land cover and other aspects of the economy. Sure, that's not there. And work with stakeholders to kind of do a kind of dynamic envisioning of the future and what it means for the different objectives that they care about. Let me get my mouse back. So I just have about 2 more slides. Back, scroll. So I also just wanted to touch on this idea of economic valuation and other concepts of value in decision making. And point out something that I think a lot of people, especially when they hear about ecosystem services or get excited about it, kind of leap to this idea of monetary valuation. And there's a set of people for whom that's like the main purpose, but there's also like a million papers talking about why you don't want to do that. And so the way I like to think about it in a somewhat bigger picture way is that all of this analysis is in the interest of supporting decisions, which is about helping a set of people choose between future states of the world, or at least deciding on efforts to take to move things towards future states of the world that they prefer over others. And so I think when you look at it in that abstract sense, it helps you think about valuation versus other participatory processes and recognize that different modes of different decision processes and criteria give more or less representation or weight to different people, whether they're included at all. And also that, some people know what they value, and some people learn their values through the process of engaging in analyses like these or stakeholder processes and deliberating with people. And so all of these different methods, whether it's valuation or kind of deliberative multi-criteria assessment or just voting, they have different implications for how people are represented, how their assumptions evolve, how their preferences evolve, et cetera. And lastly, that there's this implicit aggregation problem, both across people. An individual needs to decide how they want to trade off and aggregate their preferences across different outcomes, so water-related outcomes, habitat, et cetera. And then also how people will come together with different preferences for different combinations of ecosystem services and filter into one chosen world. And just a couple good references on that. One is much shorter and one is a book. But the first one is essentially kind of pointing out, reminding especially people in the conservation world that they are doing a lot of these things and being involved in this process when they do conservation priority setting. And so being aware of it is helpful. And I think it was the last slide. So kind of from the first part of the talk, I just wanted to emphasize that this idea of process-based ecosystem services modeling, it is feasible to do it in a way that can be used in decision-making, but it requires this kind of balance and iteration to harmonize analytic capability of the people involved, data availability, and engagement of decision-makers. And that you can also extend that to a multi-objective kind of context by translating these different land use impacts into trade-off frontiers and different maps and that type of thing, which can involve using maps or not. And then lastly, uncertainty is essentially everywhere, but if you're diligent about acknowledging it and planning for it from the beginning, then you can handle it and consider its implications in a decision-relevant way. Cool. And one more plug, if you want to learn a lot more about ecosystem services and what's going on both on the technical side and also the policy engagement side, our symposium is coming up in about a month and a half, and it started 5 or 6 years ago as more of a convening of people that work directly with NatCap, and it's now sort of evolved to be a broader ecosystem services community, and we don't actually even present that much ourselves these days. It's a lot of kind of tends to have multiple tracks, some on the policy engagement side, how people are using this in decisions, and then some more technical tracks on tool development and things like that. Thanks.
And it's at Stanford?
Yes.
And so we have time for a few questions, and as we're answering questions in the room, if the people online have a question, feel free to ask it in the chat. We'll hopefully get to it.
Thanks so much for your presentation. I guess my question is, and you kind of touched on it in maybe the third to last slide on sort of all of the high-level caveats. Our independent science board member, Richard Norgaard, released a report, or a paper actually, on ecosystem services and sort of the philosophical kind of question of engaging with that sort of process and sort of the big picture issues with it in terms of inability to capture the ecological system and some of the, dynamics that are way more complex than just sediment load reduction or water quality. And like, I think related to that also the issue of working within a market-based system and the need for absolute changes versus just relative changes over time. And so with everything that you've kind of showed and walked through, I think, some of this is super valuable and could be helpful. But I guess I'm wondering on the idea in particular of absolute sort of changes, and the need for sort of a transformation, if I think especially for ecological sort of outcome improvements. Are there particular tools or aspects of this process that sort of set that bar, if that makes any sense? Thanks.
So specifically on whether you can, like, that there's a lot of policy issues that require some reasonably accurate prediction of absolute changes in the environment. Is that? Yeah, I mean, I think so. There's not a clean answer to that, but I will say that there are different tools that speak to different processes, as I mentioned, and so you know, if you need to, if you have I'm forgetting the name for like the flow ecology relationship or something that translates how the flow regime in a river affects sustainability of species or the abundance of species. That does depend on the actual numbers, right? And so you need a model that can predict that, and our models won't, for example. So if that's a kind of purpose-built, site-based type of thing, then there's other hydrology models that will do that. I guess, yeah, I don't think I have a single answer other than that there's a diverse suite of models that exist, and they all have different strengths and weaknesses, and you kind of just have to be, when you're going into a decision, so one of the things we always ask is who is going to use this and what is the thing they actually need to know. And so what we found is a lot of times they don't actually need to know the absolute change or the absolute number, but in cases where they do, you either need to have really good data and or conduct your uncertainty analysis up to wazoo to be able to make a statement there. I guess the one extra thing I would add is that it's the uncertainty is there regardless of whether you acknowledge it or not. And so you're essentially just choosing between fuzzy states of the system. And so you can kind of think through whether to act with more precaution or not, but it's not, it is what it is, and you just got to wrestle with it.
Speaking of the uncertainties associated with any kind of model, we have had the experience that it's really difficult to bridge that translation gap between the model, the tool user and the target audience for the model outputs. Mm-hmm. One of the challenges, and since you mentioned the software part in the first section of your presentation, which, by the way, was really informative because it sort of gave a little bit of infrastructure foundation for the rest of your talk. My question deals with whether you can actually immediately, through your software application development, identify what the sensitivities are of input parameters, so you can actually identify the greatest uncertainties right from the get-go as the current state of data influences your model outputs and where you need to pay particular attention to in terms of prioritizing the data collection efforts and research efforts that need to go in to fine-tuning the data input parameters?
So the short answer is no, but that's important. And definitely agree with you, and a colleague and I actually wrote a paper talking about the need to do more to integrate uncertainty assessment more routinely into ecosystem service analyses and software. You can, in the sense, I don't know if you remember the details, but there was that part on the very right of the workflow that we had the software API, then we also had the user interface. And so right now the user interface does not facilitate that, although in the long run we hope to make that more easy. But we do have essentially, circulating among us, we have a number of scripts, and then also there's a lot of pre-existing external to NatCap software, like Python interfaces and R interfaces that can wrap that process to help you do that. So SALib in Python and sensitivity in R, for example, can do that. But it's not built into our software, but our software will allow it. That makes sense.
Hi, thank you very much. I had a question probably similar to the first question. Do you know of any recent ecosystem models that have been accepted in either legal or judicial settings, let's say like an oil spill, that take into account ecosystem models? I'm aware of things with the Exxon Valdez, which is the old MMS user days, and then DSAs for species, but they're very specific to either recreational trips and or to a certain species, discounted year service acres. Do you know of any ecosystem models, though, that have been accepted in those kinds of settings?
I do not know if they are. So I'm blanking on the name, but I know there's a fairly large integrated one that's been used for the Gulf oil spill. I can follow up with you if I dig that up. And I don't know how it's filtered into like legal decisions, but I know that it has been used to look at a lot of those impacts. Yeah, I want to say it's called like Atlantis or something. Yeah, if you give me your name, I can follow up.
I'm going to check real quick if there's any online questions. Any more questions in the room? Okay, thank you very much.
Thank you.